Great, thank you. Thank you for those of you who braved the fall, the darkness to come out here. We're going to continue today on hypothesis testing, if you will, for two sample means. I'm going to start out with a review of our last class, where we covered one sample confidence intervals and hypothesis testing using the Z and T distributions. So recall that we used the Z distribution for doing hypothesis tests and for constructing sample tests when the standard deviation was known from the population, and it didn't have to be estimated from the sample. And I said you could also use it for very large N, but that's only because the T distribution converges to the T distribution for very large sample sizes. So under the condition of large sample sizes, the central limit theorem allows us to construct these confidence intervals, because no matter what the distribution of some variable is in the population, the central limit theorem told us that the sampling distribution is normal, and it told us what its mean and what its standard deviation was. The mean was the same as the population, the standard deviation was equal to the standard deviation in the population divided by the square root of the sample size. So knowing that distribution of the sampling means allowed us to give the interval in which for the observed mean we would, or for a population mean, we would expect 95% of the samples to have their means fall within, or to construct a confidence interval for what the true population mean is based on our observation in a single sample, using this formula involving the mean of the sample, the 95% critical value from the normal distribution, and the standard error. So we could construct confidence intervals, and we could also perform a hypothesis test, and you learned that those are in a way equivalent. You get the same answers using either approach, whether it is by whether the confidence interval contains the value of the mean under the null distribution, or whether this value of Z that you calculate from your sample mean and the hypothesized mean under the null distribution falls within where 95% of the area in the standard normal distribution says you should expect it to fall 95% of the time. So we used that standard normal distribution when the standard deviation was estimated from, or was known from the population, but when it's estimated from the sample, you can do similar procedures, but using the T distribution. You can construct confidence intervals for the credible range of the population standard, or the population mean, and perform the single sample hypothesis test in the same way, except that you're using the T distribution instead of the normal distribution. So we're going to extend these concepts into two sample hypothesis testing today. And you're going to learn to apply these same ideas and these same calculations to instances where you have two samples instead of one. And the first thing that I will want you to recognize in this context is whether your samples are so-called paired samples, or dependent, paired or dependent samples, or unpaired independent samples. just to, and I'll give you some examples and details, but in general, these samples are paired when you have, when there is some natural way where one observation in sample 1 is connected to a single observation in sample 2. For example, twin studies, for example, measurements on the left and right eyes of individuals, somehow where each of the observations from the 2 samples are paired. And they're unpaired when that is not the case, when there is no way that observations in the 2 samples are connected to each other individually. Those are some examples of unpaired measurements. These are 2 independent samples. They could be things like the birth weights of unrelated boys and girls, laboratory results from 2 different participants in a clinical trial. By that I mean these are different individuals in 2 different arms of a clinical trial, or let's say comparison of household health costs in the US versus Canada, where these are unrelated individuals or locations or households that are being compared. A few examples of paired or dependent measurements could be differences in the birth weights of twins, before and after laboratory results for each participant in a clinical trial. So as opposed to them being different participants in 2 arms, for each in one arm of a clinical trial, having observations before and after the intervention. Left and right eyes of the same subjects. Stress measure scores in husband-wife or twin pairs, or measurements from 2 methods of making a measurement on a single sample. These are all examples of paired measurements because there are obvious, there's some thing connecting the 2 measurements, whether it be a patient or a specimen. So these should be easy by now, but I thought I would ask you a few questions. So let's say we have measurements that are made to compare the average heights of males and females from a sample. Paired or not paired? Not paired, very good. To compare the anxiety level of individuals before and after an intervention. Paired. Paired, excellent. To compare anxiety levels of 2 groups, one with and one without intervention. Not paired, these are 2 groups. So not paired. So if there is no natural pairing of your observations, you cannot use a paired test. You wouldn't even be able to, because you wouldn't know how to match up the observations from the 2 groups. But if there is a pairing, then you must use the paired test, because these are not independent samples. So the paired test is the appropriate test. It is the one that accounts for the fact that these are measurements on the same individual. They're not independent samples. Yes?
So on the last slide, an example of the paired was like a husband and wife stress levels.
Mm-hmm.
I'm a little confused why that would be paired and the 2 groups with the same intervention would not be.
The idea with the 2 groups with the same intervention is that they're independent groups. Okay. So, I mean, if short any more measurements, like in this example, if these were, one group of married men and another group of married women, that's not a paired design, but if they're actually household pairs, then it's a paired design. The idea being that there is some correlation between their stress levels because they're from the same household.
So the intervention doesn't connect in any way. The idea, yeah.
Yeah, it is possible to have multiple levels of pairing, like husband-wife pairs before and after an intervention. This is also possible. These paired sample tests are actually no different from the single sample tests that you learned last week. And so they're very straightforward. With a one sample, for example, the one sample z-test, your test statistic was the sample mean minus the population mean under the null hypothesis divided by the standard error. With the paired samples test, it is the same except that your numerator is the mean difference between your pairs minus the mean difference in the population under the null hypothesis. So instead of these just being observations on a single subject, the unit of observation is the difference between the pairs. So that makes it pretty simple. The procedure would just be to, if you had your observations in two columns, take the difference between those two columns and perform a one sample test on the differences. That's all there is to it. Similarly with the confidence intervals, whereas with one sample you constructed a confidence interval from the sample mean and standard deviation. With the paired test, you construct a confidence interval with the mean difference in the sample and the standard deviation of the differences divided by the square root of your number of pairs, give you a standard error. It's nice, you get almost something for free here. You get a new procedure that is essentially the same as one you've already learned. Let's go through an example. This cell phone study, for which we have some hypothetical data, was designed to answer a question of does cell phone use while driving impair reaction times? And this is an experimental study where students are given a driving simulator machine. So it's safe, it's just a video game. And at irregular periods during the driving simulation, they're flashed suddenly a red or a green light. And if it's a red light, they have to hit the brakes as soon as possible. If it's a green light, they have to continue going. So, so it requires a processing of some information that's given as quickly as possible. And for each subject, this experiment analyzes their mean response time for 2 arms of the trial. There's 32 students randomly assigned to the cell phone using group and 32 assigned to a control group that is not using cell phones. So it's a nice, simple, 2-sample, randomized, controlled trial.
But why it's independent? It's
oh yeah, why is it independent?
It's a randomized controlled trial.
Mm-hmm.
So the 2 arms are compared.
Why is this? So in this particular design, these are independent samples. Why is that? It's a very good question. Any ideas?
Because they are different groups.
Yeah, there are different people in each group.
But it's the same experiment. The experiment is applied on both of the arms or both of the groups.
Right. It's the same. Well, one arm is a control arm, and the other one is a treatment arm. So it's not the same. It's not the same treatment given to each group. It's a different treatment given to each group, and our hypothesis, our null hypothesis, will be that there's no difference in the mean response times of those two groups. But the key reason that this will be two independent samples is because they are two different groups. So
if we're estimating the difference between two groups while applying the same treatment, then they will be paired.
If it is the same treatment given to two groups, then it's really one group.
Okay.
There's no randomization then. Yeah, you wouldn't do a hypothesis test unless there is some difference between the groups.
So all randomized clinical trials will be independent groups?
Not all, no. There are case-only clinical trials. There has been an example of one of them in the news recently around gene-drive immunotherapy for leukemia, for some type of very lethal leukemia, where in a placebo group or a standard of care, there is such short survival time that they did a case-only clinical trial where everyone in that trial received the treatment. And that is based on knowledge of the population, of what the population outcome is. So they're comparing one arm to a population. So not always. There are some complicated clinical trial designs too, but your standard classical clinical trial design is two groups, a placebo or a control and a treatment. While we're on this slide, jumping a little bit ahead, how could you have used these 64 students in a paired design instead?
Paired design?
Yes.
So they are independent. How can they all be paired?
You could redesign this. You could redesign this experiment in a way that would be a paired design.
The same people, but by using the mobile and not using the mobile phone.
That's right. So in this design, everyone goes through the driving simulator once. In a paired design, everyone would have to go through it twice, once with using the cell phone and once without using the cell phone. There would be an additional consideration in the paired design, in that you would, I think, also want to randomize which they did first, whether they did the cell phone first or the no cell phone first, so that there wasn't an order effect, or at least on average, there wasn't an order effect. So here's a box plot of the results from this hypothetical cell phone study. But the mean response time for each group is 585 milliseconds for the cell phone group, that's on top here, and 533 milliseconds for the control group. So looking at this box plot, you see a fair bit of overlap between the two groups, but you do see what looks like an average larger or higher response time in the cell phone group, and you see one outlier up here. What would you say is a possible reason for this outlier, or some possible reasons? Just throw a few out there. There's lots. Give me a few.
What's the question, please? Exactly.
There's an outlier here with a much higher response time, like twice as high as anyone else. What are some possible reasons that that could happen? If you were looking at this data set and you had to give some plausible reasons and maybe go back and investigate whether any of them were the actual reason.
He was sleeping.
He was sleeping, yeah, maybe. Yeah.
Maybe this was their first, like, look at what point in their test. Maybe it was the first one and they didn't know what the break was.
Yeah, maybe they didn't understand the instructions. Yeah, didn't know where the break was. Yeah. Could have been a malfunction. Could have been they had bad eyesight and couldn't see the light go on. Could just be that they're a very slow moving person. We don't know, but we only have one observation for that person, so we can't say whether they are always really slow or just in this particular situation. Maybe they're having a really good conversation. So another thing I notice about this is it looks like the variability in these two groups is pretty similar, ignoring this outlier for that purpose. But for the bulk of the participants, the variability is pretty similar. So this is a proper two-sample design. We have a treatment and a control. They have potentially different population means. That would be the mean of all people taking, responding to the red lights who take this driver's test, whether they are undistracted or in the treatment group, which is using the cell phone. And our null hypothesis for this example will be that the mean response time for these two groups are equal. So you should be getting accustomed to writing down null hypotheses that look like this, and accustomed to what a null hypothesis looks like, so that if I give you a design like this, you can immediately go and write down what the null hypothesis would be. The second way you can write down this null hypothesis is that the difference in these two means, or the means of these two populations, is equal to 0. And what I'm noting here is that our null hypothesis is about the difference in these means. It's not about the difference in the individuals. It's about two population means being equal. So unlike the paired test, unfortunately, the formulas for calculating your test statistic and your confidence interval are a little bit more complicated for the two-sample case. But they're still not too bad. So we're using the normal, well, we're calculating a z statistic here. Recall that for one sample, it was the sample mean minus the population mean divided by the standard error. It's something similar with two samples, except that on the numerator, we have the difference in sample means minus the difference in population means under that null hypothesis, divided by this pooled standard error, or the standard error on the differences in the sample means, which under this pooled standard error is just a weighted average of the standard deviations or the variances from the two samples. I should have written, let me see, where is this? I should have written down sigmas here. Yeah, I got it right on the second part, but I wrote an S instead of a sigma up here. Make sense? Same approach when our standard deviations are estimated from the sample, except that our sampling distribution then will be a t-statistic. It will be according to a t-distribution instead of a z-distribution or a standard normal distribution. So one more calculation related where these standard deviations are pooled. Sorry, that previous one was for using the individual standard deviations. You see, we had S1 and S2, the two standard deviations in the calculation. But in a pooled estimate, you have this SP, which is a combined variance, which starts getting kind of complicated to calculate, but this calculation of the t-statistic is the same, except you get a different formula for calculating this pooled standard deviation. I don't think we're going to ever actually make you calculate this yourself. You'll be allowed to use software to calculate these statistics. A lot of potential for error if you're typing all of these into a calculator, but at least you'll know where they come from. So I've given you two approaches. One where you are assuming that the standard deviations in these two groups are equal, and another one where you don't make that assumption. Now, pooling those standard deviations it is more powerful as long as those population standard deviations actually are correct. But it can increase your type 1 error rate if it is not correct. If you're not sure, generally not pooling is the safer assumption. I don't know, this is a rule of thumb not to pool if S1 and S2 are really different, like more than a factor of 2. But on the other hand, if you have one of your samples being very small, then your estimate of the standard deviation is going to be very inaccurate. So if N1 or N2 is less than 5, especially if it's like 2 or 3, then you really should pool, unless you have a good reason not to, because you can't estimate the standard deviation well from a sample that small. So if you have big enough samples and they have very different standard deviations, then definitely don't pool. But if you have any very small sample sizes, then it is smarter to pool. You actually can end up also with type 1 errors, elevated type 1 error rates if N1 or N2 are very small, like if it's only 2 people in one of these groups. But on the other hand, with the pooled standard deviation, your degrees of freedom is simple. It's just your total sample size minus 2, because there's 2 means being estimated. But if they're not pooled, then your degrees of freedom is something complicated and it's not an integer. We give you this little shortcut that is a conservative estimate that you can use instead of that, where if you are not pooling, your degrees of freedom can be estimated as just your smaller sample size minus 1. It's not exact, but if you reject your null hypothesis under this estimate, then you'll certainly reject it using your exact calculation of degrees of freedom as well. This usually isn't a problem, though, because you are going to get this non-integer t for free from your software. Let's go through that 5-step hypothesis test for the cell phones example. In step 1, we choose alpha to be 0.05. In step 2, write down our null hypothesis that the difference in means, population means of these 2 groups is equal to 0. The alternative being that that difference in population means is non-zero. Notice that even though my scientific hypothesis here is maybe that cell phone use increases response time, they still use a 2-sided hypothesis test. And I know it's really tempting to use a one-sided hypothesis because you can't imagine how using a cell phone would result in faster response times. But you should resist the urge and just use a 2-sided hypothesis test. In step 3, go ahead and calculate our t-statistic by the sample mean, the difference in sample means divided by the standard error, and calculate a p-value or compare that to the critical value. This was done with software so that we got an exact p-value of 0.011, and since that is less than 0.05, or because our value of t exceeds the critical value for 56 degrees of freedom of 2, we reject H0. So you know whether this was using the pooled or the unpooled standard deviations here, based on what I told you in the past couple of slides? Are these pooled or unpooled?
Unpooled.
Unpooled. You still think so?
Actually.
Why unpooled?
Unpooled because they are the same sample size, and the standard deviation is not that much different.
So if the standard deviation is pretty similar, why not pool?
Pool?
I think this is pooled because we have an integer number of degrees of freedom. If it was unpooled, this would be 56 point something. So we reject H0 because we have a p-value less than alpha, and because we have a t-statistic greater than the critical t-statistic, and put this in the language of our study, which is to say we conclude that the mean response time of cell phone users is significantly different, and it is greater than it is for the control group. Nice and tidy. So let's do that other study that we suggested before. with dependent samples. So in this study, instead of the way we had it, where one group used cell phones and a separate control group did not use cell phones, we instead have reaction times measured for the same subjects at one time when they're using the cell and another time when they're not using the cell phones. So what would be, I don't know, some advantages or disadvantages of this paired design? Yep.
You might be able to more clearly tell what they're testing. So, like the subjects might be able to affect it.
Subjects might be able to affect it.
Like they'll kind of guess what they think the results might be, and it might make it more dramatic, or they'll try harder with this outcome to pay attention.
Mm-hmm. Well, that could happen. That could happen in either one because it's not blinded in that they know whether you know, unless somehow there were some deception involved and they don't know what the purpose of the study is, then they if there's no deception, then they would know whether they're in a control group or they're being studied to see whether cell phones are slowing them down. But there could be ways around that, and it is permissible. You've probably all taken your responsible conduct of research by now. You know that under certain circumstances it is permissible to use deception in a study. So maybe this would be one of those instances where you make up some other reason that you're doing the studies rather than telling them it's to study the effect of cell phone usage. Yeah.
So to make sure, the question is why we are making paired using.
Yeah. What advantages or disadvantages might a paired design have? Yeah,
the advantages, in my opinion, in this particular situation, is that we're using the same subjects, so we are neglecting the individual errors or the subject error.
Mm-hmm.
So they are the same group who will be the control and the intervention. So there's no difference between the subject or individual difference.
Right. So you're taking the sort of individual baseline reaction response out of the differences. So you're removing a source of error between the treatment and the control groups. Yeah, that is an important reason for choosing the paired design, because you have natural variability. You know, some people are race car drivers and some people are elderly. There are big differences just in their response time, regardless of whether or not they're using a cell phone. So that is a source of variability that is just error. That is not related to cell phone usage, that can be eliminated. So potentially it's a more powerful study design to use the paired design here. Did you have something else?
I was thinking that maybe, I'm not sure anymore, but a disadvantage might be that since once you do the test the first time, you get some experience. You're not fumbling, or you're not like you don't know where the break is, and then the second time you might just do better just because of that experience.
It's a very good point. So in this paired design, everyone is doing the driving simulator twice, and their performance the second time they take it might be different just because they have experience with it, and maybe they start getting the hang of it, they get better at it, or maybe they start getting bored and sleepy because it's dark and they get slower. You don't know. There could certainly be some effect of the order in which they take it. So you could probably control for that, though. Any thoughts about how you could control for that order effect?
I think when you mentioned the beginning, randomize the order in which you take the test.
Yeah, randomize the order in which you take the test. And in fact, then that order, so just randomizing the order would ensure that the order is not confounded with the treatment. So if you always did no cell phone followed by cell phone, then order is confounded with treatment. If the cell phone responses are slower, you don't know if it's because they're using a cell phone or because they're more sleepy and doing it more slowly. Or if there's no difference, it could be because there are two competing effects, cell phone making them slower, experience making them faster. Whereas if you randomize, or even if you just assign half of them in your randomizing, you would probably want to balance it so that half of them are using the cell phone first and the other half are not using the cell phone first. Then you could actually use that order as a factor in your equation when you do the analysis. And you haven't learned any multivariate analyses yet. You'll really get into that next semester. But in your analysis under this case where each individual both performs the test with and without a cell phone, and we record which of those they do first, you would have your two measurements for each individual, whether they were using a cell phone or not, and you would have an additional thing recorded, which is which one did they do first. So you could actually estimate the order effect and the cell phone effect. And that would have the additional advantage of, even if your order is randomized, so it's not biasing your results, including order in your analysis would remove it as a source of variability, of unexplained variability, because you'd be explaining any difference that occurred with order. So in this one, instead of using 32 students in each group, so we're just using 32 students in total, and for each one we have 2 observations. Oh yeah, so no one offered any, well, there was one offer of a potential disadvantage. Another one is that it's more demanding on your participants. You're making them take the test twice. So it's going to take them twice as long to do the study. So you're getting more information from each participant. The trade-offs of that might make it worth it, or they might not. Probably in this case, it's more difficult to recruit 64 students than it is to recruit 32, even if you need those 32 to stay longer to take the test twice. But that's a consideration.
Time consuming?
Yeah, it's more time consuming to have them take the tests twice. So in this case, I have 2 observations on each student, their reaction time when they were using the cell phone and when they were not. And I calculated the difference in each of these. So we have these distances and then are going to use our Z or our T method, probably our T method in this case, for one sample. Let's go through those steps again. I added a step 0 here to come before step 1, which is to choose an appropriate test and assess the assumptions. I assumed before that you had already chosen out a test based on the experimental design, and then we're just carrying out the hypothesis test. But I just wanted to point out that this is part of the process, choosing your appropriate test. In this case, we have a quantitative variable, continuous numeric variable, and it is a difference between cell phone when they're using the cell phone and when they're not. So we're using the paired sample t-test for the means. We will make the assumption here that these difference scores are approximately normal in the population, and of course that our data are obtained using a random process, or in this case that our students represent a random sample from the population of students that we're interested in. Alpha equals 0.05. Now our null and alternative hypotheses look like that for the paired or dependent samples test, where the mean value of the differences, the population mean mu, is equal to 0, and the alternative is that those differences are not equal to 0. Computer test statistic, which works out to 5.46. We have fewer degrees of freedom now, but this is much greater than our T critical. I should put T here, not alpha. Just looking on this test, let's see if I can zoom in here. So for 31 degrees of freedom, let's just look at 30 at a 95% confidence level. The critical value of T is 2.04. So 5.4 is much greater than our T critical, so we reject H0. And as a note, if we calculate this 95% confidence interval using that T critical of 2.04, just the mean difference plus or minus 2.04 times the standard error, we get a confidence interval of 32 to 70 milliseconds. Because that doesn't include 0, the no difference, you could also use that to reject the null hypothesis. Note that this confidence interval is on the difference in reaction times. I mentioned to you before that you never calculate two different, for a two samples test, you never calculate two different confidence intervals and look at whether they overlap or not in order to test the hypothesis that their means are different. Because you can have overlap in the confidence intervals and still reject the null hypothesis. Does that seem intuitive or unintuitive? So you have two confidence intervals that look like this, and you still reject the null hypothesis of no difference between the means. Remember, I showed you just earlier today, how to calculate a confidence interval on the difference between the two means. I didn't tell you to calculate confidence intervals on the two samples separately, but how to construct a single confidence interval on the difference in the two means. Looking at the box plot for the difference in the means, now it's just a single box because it's a difference. See a little bit of a skew, doesn't look too bad though. I'm not worried. N equals 32 is a fairly large sample size, and our t-test is pretty robust to violations of the assumption of normality. And there are no severe outliers here. So if you did have someone who is just generally very slow. Maybe they're someone who just doesn't pay attention normally. You would expect that to affect them both when they're using the cell phone and when they're not, so that the difference would not be, their difference would not be as much of an outlier as an observation just on them that is not a comparison. To summarize, when you have two samples, you have to decide whether they are paired or whether they are independent. And if your variables are continuous, you just take the difference between those paired observations and use the one sample t or z test. If they're proportions, it's a little bit more complicated. You can use logistic regression methods for this, which you will get into next semester. For the two sample independent tests, you have now your two sample t-test for the difference between the population means, and you have your formulas for calculating the t-statistic or the z-statistic for two samples. If you have two independent proportions, your null hypothesis will be on the difference between the proportions in the population. Or if you have a binary variable, then the average is the proportion, and hypothesis will be on the difference between two proportions. And as long as they're reasonably large, you can use the one sample normal distribution methods, the Z methods. So, told you this already, but just to try to hammer it home, when you're constructing a confidence interval for the difference of means of independent samples, this is an equivalent way to perform a hypothesis test where you accept your null hypothesis if 0 falls within the confidence interval and reject if the confidence interval does not include 0. And if you accept the null hypothesis because your confidence interval contains a null value, then you consider it that it is plausible that the proportions are equal. But if you reject, then if both your if you reject your null hypothesis, then you would infer that your two population means are different, and that one of them is greater than or less than the other. But we do this by constructing a single confidence interval for the difference. All right, some summary information for you. We've been over all of this a few times already, but for unpaired measurements, you now have your independent samples tests for two samples. For paired observations, we consider these units of the pairs and do tests on the difference. But so the units are pairs, but each of those pairs is assumed to be independent. So the two sample independent case, the two groups are independent. For the paired case, those observations are not independent, but the different pairs are independent. So there's still an assumption of independent observations in both cases. We're assuming that the population values, whether they be the observations themselves in the unpaired case or the differences in the paired case, are normally distributed, and that the independent observations are obtained by a random sample. just to make this graphical, what I have been mentioning, the equivalence between a confidence interval and a hypothesis test for the independent sample for the independent samples is based on this single confidence interval on the difference of the two means and not on overlapping of two different confidence intervals. I've given you lots of examples and neat stuff about these hypothesis tests, but I want to talk a little bit also about their limitations and about the interpretation of them. Some limitations to be aware of. First is that statistical significance, which you will assess with a p-value or by comparing to the critical value of the test statistic, is not the same thing as practical significance. When you have a small sample size, then even large, important deviations or differences from your null hypothesis might not be statistically significant. So in that case, practical differences may not be statistically significant. That is what you would call an underpowered study. You don't have enough power to reject a null hypothesis even when there's an important practical difference. Conversely, when the sample size is big, then any little difference in population means could be statistically significant, even if those differences are not especially important. And in that case, in both of these cases, confidence intervals tend to be more informative because they include both your hypothesis test that can be done just by looking at the confidence interval and how some idea of effect size or how much uncertainty is in your estimate of your outcome of interest. A little example of where a statistically significant difference may not be of practical importance is this example from a paper. It was called Too Big to Fail, Large Samples and the P-Value Problem. It's not exactly a problem, but this is this paper was talking about the relative uselessness of significance testing on very large sample sizes. And it gave this example of whether the minimum bid that eBay's sellers set for cameras has an effect on the end sale prices. And they looked at 341,000 cameras sold on eBay, did a log transformation of the minimum bid, found that it was a better linear relationship, did an ordinary least squares regression, found a coefficient of 0.1 with a tiny, tiny standard error, 0.0008, and a p-value of 0. This confidence interval goes, look at this, from 0.099 to 0.1023. So it's a tiny confidence interval on this coefficient because there's such a huge sample size. But in their step size, step 5, the interpretation would be that a 1% increase in the minimum bid is associated with an average 0.09% increase in the final price, all else held equal. So the reason they gave this example was to show that something with a minuscule p-value of 0, is probably not important to most sellers. Even if you increase your minimum bid by 10%, you still would only get something like a 1/10 of a percent increase. I'm actually not, it's a little bit more complicated there than the interpretation they give because of this log transformation. So actually, a 1% increase in the minimum bid would be associated with, this is true, but it's a multiplying factor, not just an additive factor. In BIOS 2 next fall, we'll talk a lot about multiplicative and additive models. But for now, I would just note that the interpretation is complicated a little bit by the fact they did a log transformation on their y variable. That's a bit of an aside. The main, the main lesson here is that statistical significance is not necessarily the same as practical significance or importance of the difference. Number 2, a big misinterpretation. The p-value cannot be interpreted as the probability that H0 is true. That's just a horrible misinterpretation of hypothesis testing. Or put another way, no evidence of a difference is not the same thing as evidence of no difference. Well, let's see. The p-value, when the p-value is small, let's say the p-value is 0.01, you're going to reject the null hypothesis. You reject it because what is a correct interpretation of the p-value?
That anything lower than 0.05 is statistically significant.
Sure, but what is the p-value? It is a probability. What is it the probability of?
That the sample lie in?
Sorry?
The probability that the sample or the population lie in or present in existence?
Probability that the sample lies in. Not exactly, no. This is important. What is the interpretation of the p-value? You're going to use it, so well, I do want to make sure you have a correct interpretation. Yes.
Is it the probability that there's no difference between the two?
No, it's definitely not that. That's what I'm writing down here, that it is not. It's not the probability that H0 is true. So it's not the probability that there's no difference. Yep.
Are you asking aside from probability, like, or are you asking about the what?
Yeah, what is this probability? The p-value is a probability. What is it? Like you know what it is in terms of a probability distribution. It's the area under the tails, but what is it in terms of the null hypothesis? Let's say in the example of the independent sample cell phone study, what is the p-value? What is it the probability of?
95 times out of 100, well, of the sample, I don't know.
I'm glad I stopped here. I think there's some residual confusion over this. So, yes.
Is it the probability of rejecting the null hypothesis?
The probability of rejecting the null hypothesis.
Well, the
No.
likelihood of being
No, the probability of rejecting the null hypothesis It sounds like you're almost getting ahead to power estimation. The probability of rejecting the null hypothesis when it is false is the power. Okay, well, remember the basis of hypothesis testing is that we assume the null hypothesis is true. That is our a priori assumption. Under that assumption that the null hypothesis is true, what do we calculate? We have an observation. We calculate a test statistic from our observation. And when you go ahead and calculate a p-value, how are you calculating it under the assumption that the null hypothesis is true? Let's go back to the simplest case of a single sample where you calculate the mean, and we're using the normal distribution, but it doesn't matter. What is the p-value? Remember, you calculated, this is this sample means. You figured out what the sampling distribution was under the null hypothesis. This is mu0. This is your standard error. When you calculated your p-value, you calculated the area out under the tails. Why did you calculate the area under the tails of the distribution? Do you remember doing that? Calculating the area under the right tail and left tail? Why did you do that? Yeah.
Is it like calculating the outliers, like how many outliers? I mean, not outliers, but what is 5% or whatever percent, what the p-value outside of the most of the samples.
That's descriptive of what you did, but why?
To kind of take away the outliers.
They're not outliers. Let's say, you know, this is we have, let's say these are body weights. They're normally distributed. We're taking a sample, a random sample, and we want to test the null hypothesis that the population from which our sample is taken has a mean that is equal to the greater population, mu0.
We'll not be sure from the tail, but we are sure like 95% of the population, the numbers of the 95%, that's why we're talking about these numbers, because the tails are numbers that we're not sure of any numbers.
Yeah.
I'm not sure if it's clear or not.
Let me help out a little bit here. So you learned from the central limit theorem what the sampling distribution of the means was, given that you knew the population mean and the population standard deviation. So what that allowed you to do was to say, if we're to repeat this experiment over and over, you're not going to get sample means that are exactly equal to the population mean. They're going to vary, right? They're going to go up, they're going to go down, and sometimes they'll be, you know, most of the time they'll be pretty close to the population mean, but sometimes they'll be further, you know, sometimes they'll be further out. Why? What do you call this variability? Sampling variability, exactly. And because we know the distribution of the sampling means, we know that sampling variability. And if this is at 1.96 and minus 1.96, how frequently, if we have a normal sampling distribution and we've calculated the z-scores, how often will the sample mean fall outside of these critical values? 5%. So if the null hypothesis is true, our test statistic will fall outside of these bounds 5% of the time. And that is the interpretation of the p-value. Yes, so I'll try to put it a few different ways. The one that I just said was that under the assumption that the null hypothesis is true, and we know what the sampling distribution is, the p-value is how frequently we would get a sampling mean outside of the critical means, or the outside of the critical values. So there, we set these bounds. The critical bounds are the values at which 5% of sample means are expected to fall beyond there. The p-value is the probability of getting a test statistic as extreme or more extreme than you observed if the null hypothesis is true. So if you have a p-value of 0.02, it means that, and let's say we had a test statistic of 2.5, it means that 2% of the time we would get a test statistic of what we saw or something even more extreme, under the assumption that the null hypothesis is true. And we know what the sampling distribution is when the null hypothesis is true. So key things, the p-value is the probability of observing what we observed or something more extreme if the null hypothesis is true. So remember, it's under the assumption that the null hypothesis is true. So how could it be the probability of H0 being true if we've just assumed that H0 is true? The assumption is that H0 is true. It is the probability of observing what we observed or something more extreme. So if that probability is very small, we will reject the null hypothesis as being something unlikely. So conversely, if we get a p-value of 1, does not mean that our null hypothesis is 100% likely to be true. Right? It could also just mean we have a small sample size. It's not any kind of an estimate of the probability of the null hypothesis being true. So I hope that is really clear, because it's an important interpretation. Yes.
So, like, what statement can you make out of the null? Like, you can't really. So you're saying that you can't say that a null is completely true, right?
No.
So what can you say about the null? Like when
you can either say we reject it or we don't reject it.
Oh, right.
That's about it.
I forgot about that. But like, what is that? Like, what does that mean though for somebody who looks at this? Like, so
unfortunately, you can't really say how confident you are in the null hypothesis based on a significance test. It's not really what they're meant to do. Like, because, you know, the null hypothesis is just about equality. So if you fail to reject the null hypothesis, you might fail to reject it because your sample size is not large enough, or just because that difference, you know, the difference in the means is pretty small.
Right.
And you know, in reality, you can never say that two means are exactly the same. All you can say is that we couldn't see a difference. So just like, when you write down H0 mu equal to 0, of course you like, or let's say the mean on the differences. Of course, you're not going to be able to say based on your one experience that the difference, the mean value of the difference is exactly 0. You have limited information. You can't prove that. You might be able to disprove it, but you can't prove it. So for example, researchers did not find evidence of an effect of treatment on self-reported pain level. P-value is 0.2. Does this mean that there's an 80% chance that the pain reliever has no effect? No. No, definitely not. It means that that the effect that we saw was consistent with our null hypothesis. There was not enough evidence to reject the null hypothesis without having a type 1 error rate of more than 0.05. We talk a lot about 0.05, but this is, I think, another misinterpretation of results of significance tests. In that this 0.05, it is commonly used, and it's good to have a standard that you decide on beforehand, but it's not a magic value, 0.05, between significant and insignificant. So for example, one case where this could come up is if you have 2 primary endpoints, or primary and a secondary endpoint in a study. For one of them, you get a p-value of 0.055, and the other one a p-value of 0.04. You should not interpret that as strong evidence for one endpoint and no evidence for the other one. It's actually pretty similar evidence for both of them, even though one fell just on one side of that cutoff and the other one just on the other side of the cutoff. And I would not really feel any more confident about one of the association with one of these endpoints than the other. This is a common one, especially among intro biostat students. Forgetting that significance tests are about the central tendency of the population, and they're not about individuals. They're about the mean, the central tendency. For example, researchers measure serum lead levels on a random sample of 100 children from an area with potential lead contamination. They find a mean serum level of 5 micrograms per deciliter, which is less than the normal limit of 10 micrograms per deciliter, and they reject the null hypothesis with a p-value of less than 0.01. Does this mean that fewer than 1% of children have serum levels exceeding the limit? No, it doesn't mean that. What does it mean?
That's the 1% of the population.
Sorry?
It's 1%, less than 1% of the values fall below that.
No, it's not about children. It's about the mean blood levels of children. So, yeah.
So one's referring to children's in general versus children's of that sample size that you were doing 100 children's.
Yeah, well, so give me, in terms of the discussion of null hypotheses that we were doing a couple slides ago, how would you interpret this p-value? So there's a difference in mean serum level from the normal limit of 5 micrograms per deciliter. It's 5 micrograms less. So how would you interpret this p-value as a probability?
That it's that the mean of the
Yeah.
Sorry, can you kind of like explain like what this situation is like?
So this
I know
one.
it's written, but I'm like.
So this one is the normal limit. This is not from a sample. This is, say, a regulated. Let's call this the regulated limit. So.
Right. So
the point being that this is a one sample. This is a one sample test. So.
Right.
If you were doing a one sample hypothesis test under the null hypothesis that the mean serum level is equal to the regulated limit of 10 micrograms per deciliter. It's a hypothesis test that doesn't exactly make sense. I don't know why you would want to have that as a null hypothesis.
Yeah. It's fine.
The 10 microgram is the mean of the population. So
I'm inventing a null hypothesis here. Maybe I should not say regulated, but saying that the mean in the population is 10, so that it's actually less in this contaminated area than in the population. So the let's see, normal value in the population. Normal, I can't type. Now I'm going to say that the mean serum lead level in the population is 10 micrograms per deciliter. We observe a value of 5.
So I think now we can get the z-value, and we'll see that if the z-value, it will not, the limit will not be 1.96, it will be 2.58, because it's less than 1%.
Yeah.
So if the z-value is lies between 2.58 standard deviation or negative 2.58 standard deviation, so we will accept the null hypothesis. There's no difference. If it lies out of these limits, we will reject the null hypothesis.
Yeah, these are all true, but you're getting a little bit caught up in the computational details here. So what is the interpretation of the p-value in this case? The p-value of 0.01, where the mu0 or the null hypothesis is that the mean lead level, serum lead level is equal to 10 micrograms per deciliter. What is that p-value?
If we repeat the sample 100 times, so the sample will lie between the limits that we put, which is 2.58 above and below.
Yeah, that's pretty, yeah. Essentially,
99%.
Only 1% of the time would we see a sample with a mean serum level of 5 or less or 15 or more based on sampling variability alone if the null hypothesis is true. So that means that this is a pretty outlying value. But it's those sample means that it's those sample means that only rarely exceed 5 or go lower than 5 micrograms or higher than 15. It's not about the individuals. It's about the sampling distribution. This is a confusing example.
But isn't 5 less than lead the normal is? So it's like
Yeah,
they have less lead in there.
they do have less lead.
Most people.
That's right.
Okay.
So apparently they're not being exposed to the contamination, which is possible, right? If the null hypothesis is true, and maybe there's lead in the soil, but they're not being exposed to it, then sampling variation could cause them to have an average serum contamination level above or below under the null
This is kind of
hypothesis.
important why you do it too.
Right, this is why you use a two-sided null hypothesis, because if your null hypothesis is true, the variations will be equally likely above and below, regardless of what your own hypothesis is. You're acting under the assumption that the null hypothesis is true. This is one of my favorite, that assuming because n is small, you just can't believe any results of a significance test. Or conversely, that because n is large, the results must be true. Both of these, I think, are misinterpretations. As long as you have a representative sample, a proper random sample, then your methods, the degrees of freedom, the calculation of the p-value account for sample size. And if n is small, you won't have a lot of power, but you will still have a valid p-value. If n is large, as long as it's still a random sample, that's fine, but a large sample size does not compensate for a biased sample. So your p-value will be more valid from a small representative sample than from a large, not representative sample. So what kind of error does the p-value control for? Sampling error. Very good. What doesn't it control for?
Power.
What's that?
Power?
Power is another thing. We don't try. We estimate power, but what kinds of other errors are there besides sampling error? Ways that you can have a flawed conclusion. Sorry I'm taking so long here, Tony. I don't know where the time's going. Well, study design. I mean, like that example with the cell phone study of there being an order effect. If that weren't controlled for, you could end up with an incorrect conclusion due to a flaw in the study design, and your p-value does not control that kind of error. Similarly, having a biased sample, biased measurements, these are all sources of error that are not controlled through hypothesis testing. It only accounts for sampling variation under the assumption of random sampling. That's it. Anything else, uncontrolled experiments, measurement bias, can also introduce errors that you're not controlling for. And this has caused, well, there have been numerous instances of very small p-values implying that the null hypothesis must be false when in fact the null hypothesis was true. And there were different reasons for it being rejected. This was on the cover of the New York Times back in 2011 with genomics data from cancer studies where, due to a variety of reasons that you could not necessarily tell from the paper, there were small p-values, but in fact, no evidence against, or no good evidence against null hypothesis. And the p-value, of course, it gives you a probability of rejecting your null hypothesis by chance due to sampling variation, but you can still get significant results by chance, by the very nature of it, especially if you do your study over and over again. Like if you study the link between every different color of jelly beans and acne, you might eventually find that green jelly beans are linked to acne. True effect sizes often turn out not to be as large as initial estimates. One potential reason being publication bias, where whether or not a paper is published can be related to its results. Not all research ends up getting published. And there have been some real examples of this. This reboxetine example that was passed as effective for the treatment of depression back in 2001, and then later found to be much less effective and more harmful than originally reported. And this was shown to be due to publication bias in the original trials, and this led to a whole series of changes in the requirements of reporting of clinical trials for drugs. Now, if you want to perform a clinical trial on the effectiveness of a drug, you have to register your clinical trial in advance. Otherwise, no one will consider the results of that clinical trial. That, of course, only holds for certain clinical trials, does not hold for all kinds of other clinical trials. So you have to keep that in mind. And in meta-analysis, there actually are some tests for publication bias. There can be evidence of it that turns up only later on in meta-analysis. And that brings us to an end. You should now know when to use independent and when to use paired two-sample, independent or paired two-sample T and Z tests. Identify the assumptions behind these tests, perform them, and construct confidence intervals. With that, let's take a 5-minute break and come back and do
I have a test next week. So.
let's see.